In this video, we answer a very important question about why neural networks keep improving instead of randomly guessing. So in the last video, we saw an instance where, to start a deep learning or neural network or an AI process, you have initial guesses that are guessed randomly, but then from there you now keep updating until you get what you need to get. So that's what we are considering here. Why neural networks keep improving instead of randomly guessing. So first of all, we're going to see optimization landscapes and iterative learning here. In this lesson, we will answer one of the most fundamental questions in deep learning. If neural networks start with random weights, why don't they continue making random predictions forever? Very important. So the answer lies in two key ideas. We talk about the optimization landscapes and iterative learning. So instead of changing weights randomly, repeatedly, neural networks repeatedly adjust their parameters in the direction that reduces prediction error. So this mathematically guided process allows them to gradually improve their predictions over time. So the learning objectives here, by the end of this lesson, you should be able to explain why neural networks improve instead of making random guesses. Then describe optimization as a mathematical problem. Interpret an optimization landscape like loss surface. Then understand gradient descent as an optimization algorithm. Gradient descent has been so well dealt with that by now, if you've been following all the lessons, you should already have everything you need to know about it. So then we also explain iterative learning and recognize challenges encountered during optimization, as well as understand why modern optimizers are effective. So we go. Why don't why doesn't a neural network keep guessing randomly? Big question. So a neural network begins training with randomly initialized weights. So for instance, you have W1 is 0.31, W2 is minus 1.47, W3 is 0.81, so on. So since these weights are random, the network initially produces poor predictions. However, after making predictions, the network computes how wrong these predictions are using a loss function. The loss is then used to determine exactly how every weight should change. Therefore, initialization is random, but updates are not random. So we start with an initial guess, but then we now go ahead with a guided search for the optimal solution. So every update is computed mathematically to reduce future prediction errors. So the analogy is this. Imagine walking down a foggy mountain. Imagine standing somewhere on a mountain covered by thick fog. You cannot see the entire mountain. However, you can still determine which direction slopes upward, which direction slopes downward. I mean, if you're standing somewhere and you're blindfolded, so if you place your leg somewhere, you can your body, you can feel in your body whether that step is taking you downwards, so you're going uphill. That's easy to know. So if you go, I mean, one of the easiest ways is if you go down easily. If you go easily, that means you are going downhill. But if it's hard to take that step, it means you are going uphill, right? So if your goal is to reach the valley, you simply keep taking small downhill steps. So eventually you reach a low point. So training a neural network follows the same principle where the mountain height talks about the loss, and downhill direction is negative gradient. The valley is the minimum loss, which you're actually looking for. And the small step you are taking is your weight updates. So training as an optimization problem, then training is fundamentally an optimization problem. I mean, the whole idea of AI or machine learning or anything like that is an optimization problem. So the objective is to find a set of weights that minimizes the loss function, right? So mathematically, you want to find W such that you want to find weights such that the loss as a function of weight is as small as possible. That's the problem statement. Here, W represents all trainable weights. L of W represents the loss. Training is therefore a search for the best parameter values. So imagine example, a simple optimization problem. So you have a simple optimization problem. Okay, let me go step by step. So suppose the model contains only one weight W. So let the loss function be, of course, in AI, the weights are thousands or even millions sometimes. So it all depends. So let the loss function be L of W, which is W minus 3 raised to power 2. So suppose the current weight is W equals 8. So already, if you have a loss function like this, it's already probably easy for you to know the least value. So I mean, if you do as a maths person, right? If you do maths, you can easily differentiate that and equate to zero and solve for the values. But another thing you can do is to plot. So W minus 3 raised to power 2, that's we can use W minus X here, raised to power 2. Oh, okay. This is X minus 3, actually. X minus 3 raised to power 2. So you can already see the minimum point. The X value here is 3. So the minimum loss should be 3. So we already have that idea, and we can see that from here. So suppose the current weight is W equals 8. So the loss becomes 8 minus 3 squared, which is 25. So if the weight moves closer to 3, we have W equals 6. So we are minimizing the loss like that. So then we can say that L, which is 6 minus 3 squared, is 9. Eventually, we get to a point where W is 3 because that's the minimum point we expect from the function, the nature of the function itself. So, and that produces a loss of 0. So our business at the end of the day is to get as close as to get a value of W that is as close as possible to 3, so that we can produce a value of L as close as possible to 0. So optimization means finding this minimum value of the parameter, and of course the value of W rather, that will give us that minimum loss. So look at the learning cycle, which we've talked about a couple of times. So the learning cycle is every iteration of training follows exactly the same sequence. You impute data, you have a forward pass, you have a prediction, you compute the loss, then you have a back propagation. We're going to look at back propagation, I think, in the next video. So then you have the gradient computation, and you update the weight, and you repeat, and you keep going like that until you get everything in place. So this cycle may repeat thousands or even millions of times until you get what you're after. So let's talk about what an optimization landscape is. Now, suppose we calculate the loss for every possible value of a weight, for every possible value. So each weight corresponds to one loss value. So if we plot them, we obtain a curve. So imagine, so if you have weight 1, 2, 3, 4, 5, 6 like this, so weight 1 corresponds with 0 loss. Weight 2 corresponds with 5 as loss. Weight 6 corresponds with 30 as loss. So you have the weight and the losses like that. So this curve is called the optimization landscape or loss surface. So the lowest point corresponds to the smallest prediction error. So maybe the lowest point somewhere around here. Then you also have optimization landscapes in deep learning. So real neural networks contain millions or even billions of parameters. So not just one parameter. So instead of one variable, L of W, we can optimize L of W1, W2 up to Wn. And that's where computation becomes is a very important issue. So the optimization landscape therefore exists in an extremely high dimensional space. So although humans cannot visualize such spaces, optimization algorithm can still navigate them using gradients. So gradients are so important. So now the question is why random search is impossible. Of course, we have a random initial guess, but then random search afterwards is not possible. Suppose a network contains only two weights. If each weight has 1,000 possible values, the total number of combinations will be 1,000 by 1,000, which is 10 raised to power 6. Now imagine a neural network with 10 raised to power 8 weights. The number of possible combinations becomes astronomically large. So trying random combinations will take far longer than the age of the universe. So instead of random search, neural networks then perform a guided search. So you have a random initial guess followed by a guided search to make the system efficient and to save time and space. So time and memory. So gradient descent comes to the rescue. So gradient descent is the algorithm that guides this learning, right? So you start with a random guess, and then you continue with a guided search using gradient descent, which we've talked about for the umpteenth time. So the gradient tells us which direction increases the loss most rapidly. So to reduce the loss, we move in the opposite direction. The update rule then is the new W is equal to old W minus eta times the gradient of the loss function, where W represent the weights, and I mean eta is the learning rate, and the gradient of L is the gradient of the loss, like that. So a very simple example, suppose W is 5 and the gradient of L is 4 and the learning rate is 0.1. So the new value of W this is just for a single parameter, by the way. So that's 5 minus 0.1 times 4, that's 5 minus 0.4, which is 4.6. So the weight has moved toward a lower loss region this way. So from 5 now, it's moving towards something smaller. So it's always going to be decreasing. So that's why it's gradient descent. Now, why does the gradient point toward better solutions? Why exactly does that happen? So imagine if you consider L is W minus 2 squared, of course the minimum point here will be 2. So its derivative is dl/dw, which is 2 into w minus 2. Suppose w is now 6, so you have 2 into 6 minus 4. 6 minus 2, which is 2 times 4, 8. So the gradient is dl/dw, which is 8. So since the gradient is positive, okay, since the gradient is positive, the gradient descent subtracts it, causing the weight to move left. If instead w were to be 0, then you see that dl/dw will be minus 4. If you put 0 here, so dl/dw will be minus 4. So subtracting a negative value moves the weight to the right. So thus, gradient descent automatically moves towards smaller loss values. So because smaller loss values are necessary for us to keep going in the right direction. So in the last video, right, I did it. One of uh, the problems I solved was so we saw that it was increasing because the minimum value was 4 for the function. So the function determines the direction in which things should go. So in this case now, the minimum value I believe is going to be 2. So whatever you get, every iteration is going to take you as closer and closer to 2 as you go. So we talk about iterative learning next, where we see that neural networks do not learn everything in one update. So instead, they learn through many small improvements. So you have prediction, you compute the loss, you adjust the weights, and then you have a better prediction, rinse and repeat, and you keep going until you get what you want. So each iteration slightly reduces the prediction error. After many iterations, the accumulated improvement produce an accurate model. So this gradual improvement is called iterative learning. So iterative learning is the gradual improvement you have in the process of predicting the right result and adjusting until you get exactly what you expected to get. So example of iterative learning will be something like this. Suppose top y is 10, that's the actual value is 10. The model predicts y cap to be w. So the loss then is w minus 10. That's y cap minus y. That's w minus 10 squared. Initially, w, if it starts with w equals 0, I mean, for this function, the smallest value is going to be the minimum value is 10 here for that loss function. So using gradient descent repeatedly produces this. So when uh, at at the original point, let's say the weight is 0, 0, and then the loss when weight is 0, so that means 0 minus 10, which is minus 10 squared. That's 100, and then you go the weight is now 4. So you have 4 minus 10, which is 6 squared 36. Then you go to the next one. If it is 6.40, the loss is 12.96. Then you keep going like that until you get to, so you see that the minimum value is 10. So as you keep going, you discover that the weights are increasing towards 10, while the loss is increasing towards 0. So as the weight approaches the minimum value of the function you are minimizing, the loss approaches 0, which is the minimum loss. Notice that every iteration reduces the loss, and that is exactly the goal. And knowing the weight you should be approaching can also help you to know. So sometimes as you see it increasing, you may be scared. The loss must be increasing, but the weight doesn't necessarily have to increase because the weight will naturally move towards the minimum value uh, of the function in which it is situated. So, and then we have the shape of look optimization landscapes. Real optimization landscapes are much more complicated than a simple bowl. So it's not just a simple bowl like we've been having. So they often contain local minima, saddle points, plateaus, steep valleys, and all that. So optimization algorithms must successfully navigate these regions during training. So just like I demonstrated in the last example. Okay, let me just refer to it. This is from the last video, by the way. So I remember drawing a mountain. So because a mountain can have many not just one low point. Okay, imagine this now. So this is a mountain range now, and this is a low point, this is a minimum point, this is a minimum point, this is a minimum point. Each of them is a local minimum, but then the lowest of them is the global minimum. So as a result of that, right, we have situations where there are different minima like that. So, so those are some scenarios that can arise. So you can have local minima, you can have saddle points, plateaus, and steep valleys. So optimization algorithms must successfully navigate these regions during training. So imagine the case of a local minima. So a local minimum is lower than nearby points, but it is not necessarily the lowest point overall, just like what I just showed you up there. So you have different minimum points, but okay, for instance, this can be a minimum point here. This is another minimum point. This is another minimum point, but this is the minimum of all the minima. So the optimizer may temporarily settle inside one of these valleys. So unfortunately, modern neural networks often contain many local minimum with similar performance, so that helps. Then we can also have we can have saddle points. A saddle point curves upward in one direction and downward in another. So it's you have something going upward and downward here. So there's a confusion. So there's no convergence per se. So near saddle point, the gradient becomes very small, causing optimization to slow down. So you have as you near the right value of the weight that gives the minimum loss, so the process usually will slow down. So then we also have plateaus. Of course, a plateau is just a flat land. Like in talking about mountains, right? A plateau is just something like this. You have this. So I mean, you have undulating surfaces like this, as opposed to, this other case that you can have like this. So you have flat surfaces like that. So plateaus are flat regions where the loss changes very slowly. So the movement down this slope or even down here is even still here is not is will be faster than moving on a plateau like that. So it's pretty slow. So since gradients are close to zero, weight updates become extremely small, making learning much slower for plateaus. And then you have ravines. So some landscapes contain narrow valleys like what we have here. So the optimizer might oscillate across the valley before eventually moving downward. So moving momentum-based optimization algorithms are particularly useful in these situations. So I mean, one of the modern algorithms is about something about momentum. Then we talk about learning rates, which we've talked about a lot already in previous videos. So the learning rate controls the size of each update. If the learning rate is too small, learning becomes very slow. If it is too large, the optimizer may jump over the minimum repeatedly. A properly chosen learning rate balances speed and stability. So that's the goal. You want to move as fast as possible to the minimum value, to the minimum loss, while ensuring that you don't jump over the solution. So just like you want to get off a mountain as fast as possible, but you don't while at it, you don't want to come crashing down. So you have learning rate illustration. For small rates, you have it going gradually like this. But for learning rates, large learning rates, so maybe this is minimum value. So sometimes you're here, you are down here, you can come back up and come here, but then this is where the value is. So that's the behavior of large learning rate. But a good learning rate will go steadily towards the minimum value you envisage, like that. Then we talk about modern optimization algorithms, like I just made mention of. So basic gradient descent is rarely used alone. So modern optimizers improve convergence, speed, and stability. So modern optimizers improve convergence, speed, and stability. So imagine optimizer gradient descent. It uses a full data set. Then stochastic gradient descent updates after every example. Mini batch gradient descent updates using small batches. And we have momentum like the one I talked about before. It uses previous update to accelerate learning. So it's more like you have a build up. So it's more like whatever you learned from the previous case, you use it this time around. So and that helps a lot. Then you have RMS prop, which adapts learning rates automatically. So learning rates are not fixed. So learning rates are adjusted based on the reality on ground. So you have Adam, which combines momentum and RMS prop. So today, Adam is the most commonly used optimizer for deep learning applications, and it combines momentum and RMS prop like that. So why neural networks keep improving? Neural networks improve because every update follows a systematic process. So you have randomly initialized weights and then make prediction. So you randomly initialize weight, then you make predictions, you compute the loss, you compute gradients using backpropagation, you update the weights using gradient descent to another optimizer, and you repeat thousands of times. So only the initial weights are actually random. Every subsequent update is mathematically guided toward reducing the loss. So you have random initial weights, and then you now embark on a guided search towards the optimal value of the weights or the optimal values of the weights, because you don't usually you have more than one weight. So so the key takeaway so far will be that neural networks begin with random weights but do not update them randomly. Training is an optimization problem, of course. The optimization landscape represents the relationship between weights and loss. Gradient descent follows the negative gradient to reduce prediction error. Iterative learning gradually improves the model over many updates. Then complex optimization landscapes contain local minima, saddle points, plateaus, and ravines. Then modern optimizers such as Adam improve convergence and stability, by as it combines momentum and RMS prop. Then Neural networks learn because every update is directed toward minimizing the loss function rather than making random changes. So it is like a guided search like that. So we have our practice problems as usual. Here you can find problems 1 to 5, and here I'll be solving problems 2 and 10. So, I'll be taking care of problem 2. Consider the loss function, the L of W equals W plus 5 squared. Find the value of W that minimizes the loss. So the value of W that minimizes the loss. The minimum value of W here, based on this function, if you equate W plus 5 equals 0, so that will be minus 5. So that's what is going to guarantee you a loss of 0. So, but and instead of just doing it this way, we'll talk about that when we solve it. So these are problems 1 to 5, and then you have 6 to 10, or even, okay, well, let me make it 6 to 10 as much as possible. So you have 6 to even 12, but focus on 6 to 10. So, like I said, I'm solving 10 also, which says, suppose an optimizer repeatedly overshoots the minimum and oscillate back and forth instead of converging. What training hyperparameters is most likely responsible? We'll talk about that. Then see problems 11 to 15, 11 to 15, and then 11 to, and then 16 to 20 finally. So let's go and solve problems 2 and 10 like I promised, and that'll be all for this video. So let's do problem 2 now. Problem 2. Pretty straightforward. It says the given loss function, the given loss function is L of W, which is W plus 5 raised to power 2. So to find the value of W that minimizes the loss, observe that a square a square is always non-negative. A square is always non-negative. I mean, what we have here is W plus 5 all square. So it's whatever happens inside, it will never be negative. So in that case, now we know that W plus 5 squared is always greater than or equal to 0, guaranteed. So with that in place, then we know that the smallest, so in that case, because it will never be greater than, it will never be less than 0. So whenever you see something squared, just know that the minimum value, the function can never be less than 0. So the smallest possible value of the loss is therefore L of W equals 0. So the loss cannot go negative. That's what that means. And this occurs, which occurs only when W only when W plus 5 is 0. Only when W plus 5 is equal to 0. I mean, we say that W plus 5 squared equals 0. I mean, it's always greater than or equal to 0. So the least can be 0. So for that to happen, if you take the square root of both sides, you have W plus 5 equals 0. That means W is equal to minus 5 easily. So that's how we get here. So W now is equal to minus 5. So it only occurs when W plus 5 is 0, and that implies that W is equal to minus 5. So if we substituting W equals minus 5 into the loss function, so that's L, that's L. Oh, what's happened there? Okay. Okay. Nice. So substituting W equals 5 into the loss function we have L of minus 5 to be minus 5 plus 5 all squared, which is 0 squared, and that is simply 0. So we get that. So no value, since no value of the since no value of the loss can be smaller, than 0, this is the minimum. This is the minimum. Therefore, the value of W minimizes that minimizes the loss is W equals minus 5. So the corresponding minimum loss is L min, which is equal to 0. So another way to do this is, I mean, for generally, generally we know that W plus 5 squared is, I mean, L of W is W plus 5 squared. So another thing we can do is we have dl dw, which is simply 2 into W plus 5. And we equate to 0 and we get W equals minus 5 and all of that. So it's about the same thing. And since it has only that value, so we can just confirm that it is a minimum point by doing second derivative, and we see again that it's always positive. So that goes. So let's go and take care of problem 10. Problem 10. So for problem 10, it says suppose an optimizer, repeatedly overshoots the minimum and oscillates back and forth instead of converging. So the question is, what training hyperparameter is most likely responsible. Okay. So to take care of that, we can say that the optimizer repeatedly overshoots the minimum and oscillates back and forth instead of converging. No, our goal is to converge for convergence, right? Back and forth instead of converging. So what happens? We see that the most likely cause is that the learning rate is too large. The learning rate is too large. So the learning rate is too large. That's like the most important thing. So the learning rate is too large. So the learning rate is like responsible, but we can add more layers to that. When the learning rate when the learning rate is excessively large, each weight, each weight update takes a step that is larger, that is larger than necessary, that is larger than necessary. So instead of moving closer, instead of moving closer to the minimum, instead of moving closer to the minimum, the optimizer repeatedly jumps from one side of the minimum to the other. So you have a scenario like this. Imagine you have the minimum here. Let's say the minimum value is here. So with large learning rate, right? Large learning rate. So you can have, imagine, you can have a value here at one point. You have another one here. You can have it here at one point. Then it jumps here, or it jumps here, or it jumps here, or here. It's just all over the place. So that's what a large learning rate does instead of converging to the point. So this whole jumping around, right? This oscillation prevents the optimizer from settling at the minimum and may even cause the loss to increase or diverge. So the question is, how do you fix the problem? So how to fix the problem? How to fix the problem. So possible solutions include possible solutions include reducing the learning rate. So you can reduce the learning rate as one way to handle that. Another solution would be to use an adaptive, use an adaptive optimizer, adaptive optimizer such as Adam or RMS prop. So those are adaptive optimizers. You can also use momentum, which is another optimizer. Use momentum, which helps damp oscillations and smooth smooth the optimization path. So that's a lot of story, right? Just to say this simple thing. The answer in short is this. The hyperparameter, the hyperparameter responsible is the learning rate, is the learning rate. So a learning rate that is too large causes the optimizer optimizer to overshoot to overshoot to overshoot the minimum repeatedly instead of converging. Yeah, and that's for this particular video. Why neural networks keep why neural networks keep improving instead of randomly guessing. That is exactly what we have seen. So we start with random predictions, and then we continue with guided search towards the optimal values of the parameters that minimize the loss simply. So again, look at questions 1 to 5. I've already taken care of question 2. Then look at question 6 to 10. I already took care of question 10. Then look at 11 to 15. And of course, 16 to 20. Let me know how helpful this is for you. And if there's something else you're going to try out, feel very free to let me know. So, if you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Why not go ahead and subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges that you'll find out as you click. So become a member of the channel and let's have a beautiful community together, learning maths, learning AI, learning machine learning, and all of that. Don't forget also to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.